Good morning, everyone. This is Dr. S. Venkateswarlu, working as a professor of EC at IARE, Hyderabad. Today we will discussing about Parks-McClellan filter design algorithm. So it's related to what you call uh, digital filter design aspects are involved here. Already we have seen that previously. Okay, with this there is a optimum filter design. So the windowing method is simple. Already we have seen that all using the FIR filter using the windowing method techniques. So based on that, windowing method is simple. It is not the most effective. So this is somewhat it is what you call drawback or maybe a disadvantage. So where it is the windowing method is simple, where it is not the most effective. If you are using that rectangular window, is optimum in one sense, since they minimize the mean square approximation error to desired response, but causes errors around discontinuities. So we can consider this is the one disadvantage. Other thing is most popular alternative method is that is today's topic on what you call Parks-McClellan algorithm. Okay, so this uses minimax error method for function approximation. Okay, so that is the background of today's topic on Parks-McClellan filter, maybe background or design algorithm. Okay, so with this different methods of optimum filter designing by approximation, here also we have to recollect this one. So methods of optimum filter designing by approximation. Weighted least squares method. Initially we have to use this particular popular method. Okay. Second one is Chebyshev method, or we can consider the Adolph-Chebyshev method, and one more WLS Chebyshev method. Other important algorithm is famous algorithm is today's topic, that is Parks-McClellan what you call filter, or we can consider this algorithm using this filter design algorithm. Finally it is compress this one, Parks-McClellan filter algorithm. Okay, so here Parks-McClellan often called the Ramage exchange method. This is the one way. This method design an optimal linear phase filter. This is the standard method for finite impulse response design. Okay, so this is the background. So how we are chosen, how we collect this particular what you call algorithm. Okay, so with this now we have to enter this one, this methodology for designing symmetric filter that minimize. So what we have to minimize the filter length for a particular set of design constraints, where omega p, omega s, pass band or stop band, and delta p, comma delta s. Okay, the computational effect is linearly proportional to the length of the filter. Okay, or we can consider that out of the filter and so on. This is one aspect. Other thing is the MATLAB. This method is available as a Ramage pair parenthesis. Okay, so with this, so Parks-McClellan method, the resulting filter minimize the what you call the maximum error between the design frequency response and actual frequency response by what you call spreading the approximation error. Okay, uniformly over each band. Okay, this is one aspect. Other thing is such a filters that exhibits equiripple behavior. Okay, in both the pass band and the stop band, and are sometimes called equiripple filter. There is a possibility while you are using this type of algorithm or methodology. Okay, you will expect this all outcome of this. Okay, So alternative theorem, or this polynomial of the degree L that minimize the maximum error will have at least L plus 2 what you call extrema. Okay, and the optimal frequency response will just touch the maximum ripple bounds if you are using this all analysis. Okay, so the extrema must occur at the pass and stop band edges, and at either omega equal 0 or pi or both. Okay, so using this all constraints, we are to implement this alternative theorem. Okay, now the derivative of the polynomial of the degree L is polynomial of the degree L minus 1, which can be 0 in at most L minus 1 places. So the maximum number of here we can consider that polynomial is L. The polynomial is L. L is a polynomial. Okay, where L is the polynomial of the degree is in terms of L minus 1. Okay, so with this, which can be 0 in at most L minus 1 places. Okay, so the maximum number of local extrema is L minus 1. Okay, local extrema has extrema plus the 4 band edges. So that is after using this first band and the second band and third band, finally that is going to be L plus what you call L plus 3. Okay, so the alternation theorem does not directly suggest a method for computing the optimal filter. Yeah, this is the way for derivative of the polynomial of the degree L with help of L is a polynomial of the degree L minus 1, which can be 0 in at most L minus 1. So the maximum number of local extrema is L minus 1. So local extreme plus 4 bands. Okay, first, second, third, and fourth band. 4 band edges. That is going to be what we call L plus 3. Yeah, the alternation theorem does not directly suggest a method for computing the optimal filter. Okay, now, if you are using this implementation of this particular theorem, you see this all. Okay, after once we are collecting this background history of this particular algorithm design aspects, after that we are ready to implement by using the particular algorithm or maybe step-by-step procedure. After that, we will ready to write the piece of code. We will ready to what you call compile and execution. We will expect our what are the expected outcome or maybe resultant. It is your desirable resultant are received or not. We will ready to verify. In this case, okay, filters that FIR finite impulse response filters allows the design of linear phase filter. Already we have proved mathematically and practically by using MATLAB software. Yeah, which eliminates the possibility of the signal phase distortion. Already it is proved by while you are using finite impulse response filters. Yeah, two methods of linear phase FIR filter design were discussed already. We have done here the ideal window method. Yeah, using this all ideal window method with help of what you call rectangular window or Kaiser window or Dahl-Chabichi window and Gaussian window and so on. All Kaiser windows, all we have seen. The ideal window methodology is verified. Finally, what is the outcome of this window? Yeah, there is you will observe that there is a discontinuities. The optimal Parks-McClellan method, you will see this what you call the series. Okay, so finite impulse response is a advantageous due to what you call linearity and stability. That's why always we have to use the FIR when compared to the IARE filter. Infinite impulse response filter and finite impulse response. You know that all recursive or non-recursive. Okay. The disadvantage of the finite impulse response digital filters include expensiveness, and that the process is time consuming. This is a major drawback. or we can consider these are the disadvantages while you are using what you call finite impulse response digital filters. With reference to this, we are to verify what are the importance of this and previous one. Yeah, the Parks-McClellan algorithm published by James McClellan and Thomas Parks in 1972, and alternative algorithm for finding the optimal Savichui filter, what you call FIR filter or finite impulse response filter. Okay, an alternate algorithm for finding the optimal Savichui finite impulse response filter. This way they are preferred. These two people are James McClellan and Thomas Parks in 1972. Okay, with this, the Parks-McClellan algorithm is utilized to design and implement efficient and optimal finite impulse response digital filters. It uses an indirect method for finding the optimal filter coefficients. With the help of this, we have to use the mathematically and numerical values. So we have verified. It uses an indirect method for finding the optimal filter coefficients. Okay, so with this, the goal of the algorithm is to minimize the error in the pass band and stop bands by utilizing the Savichui approximation. Okay, so this is the popular windowing technique, where it is Savichui approximation. Okay, the Parks-McClellan algorithm is a variation of the what you call Remez exchange algorithm. We will discuss that in depth of this Remez exchange algorithm. So with the change that is specifically designed for the finite impulse response digital filters. Okay, so with this, it has become a standard method for finite impulse response digital filter design. Okay, so now for in depth of this, what the background and history of this particular algorithm, like Parks McClellan filter design algorithm. So, what is the history of the optimal FIR filter design? You know that background. So, with reference to that, you can recollect these all Parks McClellan filter design aspects. Here in the 1960s, researchers with you, like you and me, within the field of analog design were using the Savichui approximation for filter design in 1960s. Okay, during this time, it was well known that the best filters contain an equiripple characteristic in their frequency response. That is, here into the frequency response, it is based on the concentrate only frequency response magnitude. Okay, and the elliptic filter, or you can consider the Bezier filter, was optimal with regards to the Savichui approximation. That time in 1960s, they are evaluated. Okay, so now when the digital filter revolution began in 1960s, okay, previously they are using only analog filters. Okay, analog filter. Now it is when the revolution is the digital filter revolutions began in 1960s. Researchers used a bilinear transformation to produce infinite impulse response (IAR) digital elliptic filters. Once it is entered that a digital filter revolution, so researchers used in a bilinear transform to produce infinite impulse response (IAR) digital filter, IAR digital elliptic filters. Okay, okay. With this, they also recognize the time. They also recognize the potential for designing finite impulse response filter to accomplish the same filter task, and soon the research was on for the optimal finite impulse response filter using Savichui approximation. That time in 1960s. Okay, so this is the brief on this optimal finite impulse response filter design. Okay, now it was well known in the both mathematics and engineering that the optimal response would exhibit, okay, would exhibit an equiripple behavior, the time only, okay, equiripple behavior, and that the number of ripples could be counted using the Savage approximation. If they are in the different techniques like what you call Gaussian irreducible escape, previously they are using that all other techniques, but using this could be counted using this Savage approximation or Dolb-Savage approximation. Okay, several attempts to produce design program for the optimum or optimal Savage finite impulse response filter were undertaken in the period between the 1962 to 1971. Yeah, there is the greatness of once we are learning this type of algorithm background, of our filter background. So, to produce a design program for optimal Savage finite impulse response filter were undertaken in the period between 1962 and 1971. Okay, so despite the numerous attempts, most did not succeed. Okay, this type of research is done that time. Okay, usually due to these problems in the algorithmic implementation or problem formulation. Okay, problem defined. Okay, so due to these particular problems in the algorithmic implementation or maybe problem defined or problem formulation or that research cap. Okay, so this scenario, okay, so auto Euronom and okay, what do you call, for example, proposed a method for designing equiripple filters with restricted band edges. With the restricted band edges. With this, somewhat it is there done that research literature survey. Somewhat the problem formulation, problem is identified. Based on that, so these people proposed a method for designing equiripple filters with what do you call restricted band edges. Okay, so with this method obtained an equiripple frequency response to the maximum number of ripples by solving the set of non-linear or nonlinear equations. Nonlinear equations. With this, okay, another method introduced at the implement this time implemented an optimal Savage approximation, but the algorithm was limited to the design of relatively low order filters. Okay, similarly to Herman's method, E.D. Hofstadter presented an algorithm that designed finite impulse response filter with as many ripples as possible. They are observed due to their research work, as many ripples as possible. Yeah, this has become known as the maximum ripple algorithm. Okay, the maximum ripple algorithm imposed an alternating error conditions by interpolation and then solved a set of equations, solved our mathematical equations are involved here, that the alternating solution had so satisfied. Using this all research work, that researchers they have done this type of work, so somewhat the alternative solution had to satisfy. One notably limitation of the maximal ripple algorithm was that the band edges were not specified as inputs to the design procedure. They're following the different aspects like using the procedure or the what you call step-by-step procedure. Finally, there is a limitation of the maximum ripple algorithm was that the band edges were not specified. Okay, with this design procedure. Rather, the initial frequency at omega I where that what do you call omega I with this, where omega I and the desired function, it is followed by d of omega I, define the passband and stop band implicitly. Okay, so with this, unlike these previous attempts to design an optimal filter, the maximum ripple algorithm used as uh, used an exchange method. Okay, using this whole work that tried to find the frequencies at omega I, were the best filter and had its ripples. Okay, here it is. A lot of ripples are there observed with the set of omega I. Okay, so this thus the maximal ripple algorithm was not an optimal filter design, but it had what you call quite a significant impact on how the Parks MC-Cleland algorithm would formulate. Okay, so this in August 1970, James MC-Cleland and entered graduate school at Rice University. So with the concentration in the mathematical models of analog filters design, and enrolled in a new course called digital filters, like our IARE and FAR. Okay, due to his interest in filter design. Okay, the course was taught jointly by Thomas Parks and Sid Burrows. Okay, with this at this time, the digital signal processing was an emerging field, and as a result, lectures often involved recently published research paper on this aspect after taught jointly by Thomas and Parks and Sid Burrows. At this time, that our digital signal processing was an emerging field. Okay, the following the semester, they have observed the spring of 1971. Thomas Parks offered a course called Signal Theory. Initially, it is identified that what we call our subject, our course, digital signal processing. After that, the following the SIMS, the what we call Thomas Parks offered the course called Signal Theory, ST, Signal Theory, which MC Cleland took as well. So this is the tremendous background, or let us say survey related to our filter design algorithm. Okay, so during the spring break of this semester, Parks driven from the what we call Houston to Princeton in order to attend a conference. This is the background while we are learning this all. There is a disadvantages in digital filter live FIR doing technique and so on. How they are overcoming this type of history or background letter surveys is we have to investigate. That's why we are talking about this much stuff related to this particular filter design algorithm. Okay, so where he had the DED Upstetter's presentation about a new finite impulse response filter design algorithm. It is going to be what you call, it is nothing but a maximal ripple algorithm. They are proposed. Maximal ripple algorithm. From that DSP2 up to signal theory 2 as well. During this spring break of this semester, Parks drove the vertical in order to attend the vertical, where he had that presentation about the new finite impulse response filter design algorithm. It is going to be, it is nothing but a maximal ripple algorithm. Okay, so with this Savichu, using this all, there is a possibility thinking about the possibility of using the Savichu approximation theory to design a finite impulse response filters. Okay, he had that the method implemented in the Hofstetters algorithm was similar to the what you call Riddle exchange algorithm. Okay, and I decided to pursue the path of using the Ramage exchange algorithm. Okay, so the students in the signal theory, they are concentrating on this particular course, were required to do the project, and since Sabishu approximation was a major topic in the course, they have to choose one. Yeah, the implementation of this new algorithm became James MC McClellan's course project. They decided. This ultimately led to the Parks-McClellan algorithm, which involved the theory of the optimal Sabishu approximation and an efficient implementation. Okay, so with this background, by the end of this spring semester, MC Clennon and Parks were attempting to write a variation of the what you call image exchange algorithm for finite impulse response digital filters. Okay, so it took about 6 weeks to develop and some optimal filter. Some optimal filter had been designed successfully by the end of the digital signal processing course in that time. Okay, that is the greatness of DSP and signal theory, and how they are chosen that all background of this particular Ramage and Parks MC-Clellan filter effects. Okay, so with this they are identifying the graphically. Okay, one is in the picture, this one we take note of these various axes here, x-axis and y-axis. So the y-axis is the frequency response. Okay, these are your frequency response. You can consider that all h of omega mod h of omega, and the x-axis are the various radiation frequencies, where we can consider that all here it is omega I, or you can consider that where omega I with the help of this easily can analyze. And the x-axis are the variation radiance frequency omega I. Okay, so we know that two frequencies marked on the axis omega p here, omega p and omega s. Okay, uh, omega p indicates the passband cutoff frequency. You know that one, omega p, where omega p and omega s. Okay, so with this omega p and omega s, okay, it indicates the passband cutoff frequency, and omega s indicates the stop band cutoff frequency. Okay, so with this, the two dashed lines. So here we are observed that are dashed lines here, omega p and what do you call, and omega s are dashed lines. Yeah, the two dashed lines on the top left, this the top left of the graph indicate the what do you call, it is indicated the omega, what do you call that, omega p, and the two dashed lines on the bottom right indicate the omega s. Okay, so with this omega s and omega p. Okay, so now all other frequencies listed indicate the extreme frequencies of the frequency response plot. These are all nothing but a frequency response graph or plot. Okay, so with this, here as a result there are 6 extreme frequencies. What are the 6 extreme frequencies? Like omega s or ETHD, omega 1, 2, 3, 4, and so on. Here then they add this and then we add the passband and stop band frequencies to give you a total of 8 extreme frequencies in the plot. What are the 8 here? Where omega 1 here, and omega 2, omega 3, omega 4, 5, and 6. Here it is omega versus that frequency response. Okay, so stop band frequencies to give a total of 8 extremal frequencies on the particular graph or plot. We have seen that right side here. Okay, this is the uh, graph, but there is a y-axis in the frequency response, and x-axis on the various radiant frequency omega 1, 2, 3, 4 up to x, or we can consider omega I. Okay, so pass and stop bands of the filter designed by the Parks-McClellan algorithm. The y-axis is the frequency response h of omega, and the x-axis are the various radiant frequencies omega I, as per this graph. Okay, so it can be noted that the two frequencies marked on the x-axis, where omega s and omega p indicates the pass band cutoff frequency, and omega s indicates the stop band cutoff frequency. Okay, so with this, the ripple, like a plot of the here, that ripples you have to verify that here in this case. Okay, so the ripple, like a plot on the upper left, is the pass band ripple, and the ripple on the bottom right is the stop band ripple, like this. Here the ripples are ready to observe in graphically. Okay, so now the two dashed lines on the top left of the graph indicates that the what you call delta p, and the two dashed lines on the bottom right indicates that delta s. Okay, this all other frequencies listed indicate the extremal frequency of the frequency response. The what you call frequency response plot. As results, there are 6 extremal frequency we have observed as per that graph. Okay, so and then we add the pass band and stop band, okay, frequencies to give a total of 8. What we have seen extremely frequency on the plot. Just we have verified the graphically. Okay, now the algorithm using this all history and what are the basics on this plot graphical representation. So ideally, what is the algorithm? Because of we have to satisfy our title, Parks-McClellan filter design algorithm. The algorithm, so the Parks-McClellan algorithm is implemented using the following the steps. Step by step, where algorithm is nothing but the step by step procedure we have to follow. Following the steps are step 1, initialization. That initialization choose an extremal set of frequencies omega I power 0. Okay. Next, coming to the second step, finite set approximation. Calculate the best Chebyshev approximation on the present extremal set, given the value delta power m for the minimum maximum error on the present extremal set. This is the second step. Coming to the third step, step number 3. Okay, interpolation. Calculate the error function. It is followed E of omega over the entire set of frequencies omega using step number 2. The step number 2 is finite set of approximation. How they are calculating the finite set approximation? Calculate the best Chebyshev approximation on the present extremal set, giving the value delta of m for the minimum maximum error on the present extremal set. Okay. Now coming to the step number 4, look for the local maximal of mod e power m of omega and the set omega. Okay. Now coming to the step number 5, if maximum of omega 4 with e of m of omega, so greater than or equal to delta m, then update the extremal set of omega I power m plus 1 by picking new the frequencies where e power m of omega has its local maximal. Make sure that the error alternates on the order set of frequencies as it is indicated with step number 4 and step number 5 required to step 2 and what you call iterate. Like this, we have to follow this all step by step. The Parks-McClellan algorithm is implemented using this five steps. After that, right, to verify that step number 6. Okay, if maximum this value mod e power m of omega less than or equal to what we call delta power m. Okay, then the algorithm is complete. Use the set of omega I power 0 and the interpolation formula to compute an inverse discrete Fourier transform. Here it is. Already we know that discrete Fourier transform, but here we have to follow that inverse discrete Fourier transform to obtain the filter coefficients. Okay, so like this, the Parks okay, this particular algorithm is extremely this. Okay, next description of this algorithm, how we are analyzing this one. So the picture above on the right, what you call right display on the various extreme frequency for the plots shown or using the graphical representation. The extremal, here we can consider that this is already we have seen. We have to consider this diagram. Okay, so usually can analyze this all, how it is happened, that how many what you call ripples are absorbed. So with this all implementation. Okay, so with this, the picture above on the right displays the various extremal frequencies for plot shown. The extremal frequencies are the maximum and minimum points in the stop and pass band. The stop band ripples is the lower portion of the ripples on the bottom right of the plot, and the pass band ripple in the upper portion of the ripples on the top left of the plot. So we have to the top picture, the plot. Based on the plot, usually can analyze the in terms of the description. The dashed lines going to across the plot indicates the what you call delta or maximum error given the position of the extremal frequencies. There is a formula for the optimum delta or optimum error. Okay, so easily can analyze in mathematically of that using this all mathematical notation. We should write that all piece of code of that the code is running using the MATLAB. Usually can expect that that graph is same or different, or what the initial or after simulation, how it is affected, how many ripples are absorbed practically or normal or standard level. Okay, since we do not know this that the optimum delta on the next what you call exact position of the extreme on the first attempt, we what you call iterate. So here effectively we assume the position of the extrema initially and calculate the delta. We then re-estimate and move the extrema and calculate delta or the error. So using this all merits and demerits, easily we will analyze using this all graph and by implementing this particular algorithm. After that, we will try to verify that all resultant. Okay, so with this, before applying the Savicio approximation, a set of steps were necessary. If you are missing this one steps, you are unable to identify your accuracy information or resultant aspect. Okay, so step 1 here we have to follow. If you are before applying that Savicio approximation, a set of steps were necessary. What are the steps? It is near to your algorithm steps. Okay, so define the set of basis function of the approximation, and step 2, exploit the fact that the pass and stop bands of band pass filters would always be separated by transition region. If you are missing these all steps, we are unable to verify this what the Savicio approximation, either it is involved or not for implementing this particular algorithm. Since finite impulse response filters could be reduced to the sum of cosines case, the same core program could be used to perform all possible linear phase finite impulse response filter. So this is the one array. In contrast to the maximum ripple approach, if you are not implementing this type of steps, the approach will not be satisfied. The band edges could now be specified ahead of the time, okay, to achieve an efficient implementation of the optimal design using the Parks-McClellan algorithm. Two difficulties have to be overcome. What are the two difficulties or merits or disadvantages here? Problems. Here one is step one. We have to follow the steps or that difficulty one. So defining the flexible exchange strategy, and okay, step two, implementing the robust interpolation method. Okay, so like this, in some cases, the programming involved the implementation and adaptation of the algorithm for use in the finite impulse response filter design. Two phases of the exchange strategy were taken on make the program more efficient. The piece of code is involved here, how it is we are exchanging, what type of syntax or other aspects, what type of built-in and without built-in function and so on. Okay, with this we have to follow this remaining steps. Step 1, allocating the extreme frequency between the passband and stopband, and second one is enabling the movement of the extremal between the bands as the program what you call iterated. So the reference is mentioned here. Due to this reference, usually you can analyze that all of them form the different what you call these methodologies or procedure or maybe steps, what are the precautions they are following. If you are missing this all things, what happens? We are unable to verify that our accuracy plot response. Okay, there may be magnitude response or maybe frequency response or a graphical representation. So at the initialization, the number of extremals in the passband and stopband so could be assigned by using the ratio of the sizes of the bands. Okay, with this. Okay, furthermore, the passband and stopband edges would always be placed in the extremal set and the program's logic kept. We have to follow that syntax of that according to mathematical notation. Should write that a piece of code or software code. Okay, the program's logic kept those edge frequencies in the extremal set. Okay, the movement between the bands was controlled by the comparing the size of the errors. Okay, or maybe number of errors at all the candidate extremal frequencies and take the largest. Okay, so with this, the second element of the algorithm was the interpolation step needed to evaluate the error function. Using this all step by step or process or identifying this using the different what you call piece of code, the program's logic kept those the edge frequency of the extremal set. Okay, so here you are right to observe that our comparing the size of the errors at all the extremal frequencies and taking the largest. Okay, the second element of the algorithm was the interpolation step needed to evaluate the error function. Okay, with this they used a method called very strict form of the language interpolation, which was very robust. Okay, like this, all conditions for the Parks-McClellan algorithm are based on sub-issue alternative theorem. That's why we are learning this all stuff, the background or description and condition. Like this, easily can analyze. The alternation theorem states that the polynomial of the degree L that minimize the maximum error will have at least L plus 2 extrema, or we have discussed. The optimal frequency response will barely reach the maximum ripple bounds. Okay, the extrema must occur at the pass and stop bands edges and at either omega equal to 0 or omega equal to pi or both. Okay, so with this, the derivative of the polynomial what you call of degree L is a polynomial of the degree L minus 1, which can be 0 at most at L minus 1 places, or we have seen L minus 2, L minus 3, and so on. But here it is specified which can be 0 at most at L minus 1 places. Okay. With this, so the maximum number of local extrema is the L minus 1 local extrema plus the 4 band edges, giving the total of L plus 3 extrema, or we have discussed. This is the conditions for the this particular algorithm are based on Sebechev, what you call alternative theorem. Okay, so like this, you have to refer this all. Of that, we have to analyze this all Parks-McClellan filter design algorithm. Till now, we have done that all background of this algorithm. Varieties are demerits in disadvantages of a digital filter using a finite impulse response filter with help of windowing technique, like maybe using the Sebechev or maybe Sebechev or Kaiser and Kalman filter and other windowing techniques, where the demerits, how to overcome this all demerits, we go for this particular algorithm. Okay.
Like, share and subscribe. Hit the bell icon for more updates.